Part B now gives us, let R be a region bounded by this line and the coordinate axes. Explains why f satisfies the conditions of the extreme value theorem on R. So let's draw a picture of R. There's x and y. So we have the line 16x plus 16y equals 13. If I wanted to graph this line, I could quickly find the intercepts. The x-intercept can be found by setting y equal to 0, so x is 13/16. So I'm going to call that 13/16 there, and it's symmetric, so we got 13/16 there. And so we have this line, and bounded by that and the coordinate axes. So this is what we're talking about here for R. And what's important about R, R is closed and bounded. Our function f was a polynomial, so it's continuous. And so we could say since f is continuous and R is closed and bounded, the EVT applies. And so f attains a maximum and a minimum on R. Alright, in part C we're asked to optimize f over R. That means we need to find the absolute maximum and absolute minimum of f. So when we do that algorithm like we talked about in class, the first thing we have to do is justify there is an absolute max and min, which we did in part B. We used the extreme value theorem, so we know this exists. The second part then is to go looking for the critical points, which we did in part A. These are the two critical points we found from part A. We need to know which of these lie in the region R. Well, 0, 0 actually lies on the boundary of R, so we're going to pick up 0, 0 as we do the boundary analysis. The point 1, 2, however, is way over here. It's outside of R, so we don't need to consider 1, 2 at all anymore. So first step is to justify the existence of the max and min. Second step, find the critical point. Now it's time for the third step, which is to analyze f on the boundary. So analyze f. Little f on the boundary. So there's three boundary parts here. We'll call that boundary part 1, call that boundary part 2, and then boundary part 3. So let's look at boundary part 1. Boundary part 1 is the x-axis. The equation for the x-axis is y equals 0. And it's not the entire x-axis, it's the portion x between 0 and 13/16. So what I do is I look at what the function looks like on that boundary curve. On that boundary curve, y is 0. So I look at f of x 0. That just gives me a function of x. And I go through there and I get 8x cubed. And once again, x is restricted from 0 to 13/16. And now what I do is I hit this with my Calc 1 stuff. So I need to optimize this function on this interval. And so I take the derivative. I get 24x squared. I look for the critical values. The derivative always exists. I set equal to 0. The only critical value I get is x equals 0, but x equals 0 is one of the endpoints. I would consider that anyway. And so then I look at the function value at the endpoint and the critical values. F of 13/16. F of 13/16 is some ridiculous number. We'll not evaluate that unless we absolutely have to. Alright, so that's the minimum and maximum on that part. So I'm going to go up there in red and put those values in. So here I was at 0, and then here I had this ridiculous number. so that completes our analysis on boundary 1. All right, we move along now to boundary 2. Boundary 2 is a portion of the y-axis. So that's the equation x equals 0. And it's for the y values between 0 and the y-intercept there, 13/16. So I look at what my function is doing on that. X is 0. I'm just going to get a function of y now. So 0, 0, I get 3y squared. And now once again, it's not the entire parabola, 3y squared. It's the portion between 0 and 13/16. So I go ahead and do my Calc 1. So I do f prime of y is 6y. This always exists. I set equal to 0. I get y equals 0, which is one of my endpoints. So I look at f of 0. I get 0. I look at f of 13/16. And I get 3 times 13/16 squared. Another ridiculous number. And so I'm going to have to put that up there on my thing. Now, this f of 0 equals 0, I really didn't have to do that because that's at this point here that I already did before, but it's a good double check. But now at this point, I've got my 3 times 13/16 squared. I'm going to write that over here. And that'll do it for boundary 2.